Howdy everyone, welcome to another lecture for CS Content 8 Honors. Today we are exploring generics and smart pointers. First, let's look at a couple motivating examples. So in Rust, as you have seen from the beginning of the class, several types can contain other types, such as vectors, arrays, hash maps, or enums like options and result. So how do they do this? And as another example, here you see two functions that both essentially take in a list of elements, compare, and return the largest elements in the list. As you can see here, is that both these functions essentially do the same thing, just with different function signatures. One compare a list of integers, and the other compare a list of chars. Say if we want to apply this same logic to other types, such as if we have a list of U16s, we also need to repeat this same code in another new function. This seems really wasteful. Can we reduce a boilerplate? So generics. Generics are basically abstract stand-ins for concrete types or other properties. And they can be used in the definitions of structs, such as a vector or enums, as we have seen with option and result. They can also be used in methods and functions. So what abstract stand-ins here basically means that you can substitute the genetic type with any actual type, such as a vec. You can have a vec identity2, vec chars, vec u16s, or any other types that you have. The similar things for options and results. First, let's look at generics in structs. So here we have an example of a struct point that contains contains a genetic type T. So from the struct signature, you can see that this we have the struct name, and then these arrows here, and a T in the middle. What it means is that this struct point contain members with genetic type T. So here you can see that both the members X and Y have the type T. So here, when you have an instance of the struct point, X and Y can be of any type, but they must be of the same type. As you can see from the code here, we have two instances of that struct. One where we have a point where members are of type i32, the variable integer here. As you can see that X and Y are of type i32 and the values are 1 and 2. And then we also have a variable float that is of the type point, but members contain the type f32. Members are of the type f32. And the values are 1.0 and 2.0. Do note that Rust will treat these two as different types, even though they all come from the same struct, because the types of the members are different between these two. So here, for example, we have X and Y be of the same type, but what if we want them to be of different types? Say a genetic type T and a genetic type U. And we can just declare the type T and U accordingly. So say as you can see from the example here, say from the example on the right, say we want X to be of the type T and Y to be of the type U. We can just put them as a type for the members. And then in the struct definition, we need to put both of those genetic types. So the function signature with the struct signature will be point, and then with T and U in between the brackets. This means that the struct point contains members with genetic types T and U. So This syntax allows X and Y to take different types. And here we come to a syntax rules for generics that the struct definition. So the point with various generic types in the middle here, you must list all generic types of members. So say we have a point X, Y, Z with types T, U, and V. You have to list all T, U, V in the struct definition. So on the example on the left, here we see an example that doesn't work. So here the struct point only has members with the generic type T, and that is both X and Y. So when you have an instance of the struct point, you cannot have the members be of different types. So X here is an integer and Y here is a float. That doesn't work. It only works if you have different generic types for X and Y. So here you can have the generic type, the concrete type for X be I32 and concrete type for Y be F32. And you can assign the values accordingly. X is 1 and Y is 2.0. Let's look at the example in code. So here is basically the example we have from earlier. We have a struct point with members of generic types T and U. X is the type T is for X and the type U is for Y. And then we declare an instance of this struct with types I32 and F64 for T and U. So since X has a type T, it could take the type I32 and can you take the value 1. Similar for Y, it can take the value 2.0. And here we will print out the members X and Y. As you can see here, it prints out X is equals to 1 and Y equals to 2, which is what we would expect. Next, let's look at generics in enums. So here you can see an example of an enum with generics. So we have the enum number here with the generic type T. So we have this. So this enum has two variants, finite number, and infinite. The finite number contains a value, and this value will be of the type T. Note the enum signature here, number with T in between the brackets. It means that the enum number contain variants that contain value or values of type T. Since the variant finite contains a value of the generic type T, we have to put T in the enum signature. And here we create two instances of this enum. A finite instance where that is where the enum number contains a generic contains a concrete type of type I32, and we assign that the value finite 5. And the other an infinite number, also of the same enum and a different concrete type. This time it's U32, and we assign the value infinite. So do note here that even if we use a variant not containing the type T, so in the second example here, we use a variant infinite which does not contain a value of type U32, we still need to declare the concrete type for T. So we still need to declare the concrete type U32 here. And similarly, we can have multiple concrete types, multiple generic types. So we have another enum number here with generic types T, U, and V. It has 3 variants. a one-dimensional finite number that contains a a value of genetic type t, and a two-dimensional finite numbers that contains two values of genetic types u and v that allows them to be of different types. And we see a similar syntax to the struct example. Number with all of the genetic types in declared. This means that enum number has variance containing values of type t, u, and v. And as you can see here, our variants do contain these types. And here we see three examples of that enum. Both are of the enum numbers, and both contain values of type I32, U32, and L32. One is a one-dimensional finite number containing the value 5, which is of the type I32 here, so it's valid. And the other is a two-dimensional finite number with values 2 and 1.0. And since our U and V here, we put the concrete types U32 and L32, the values 2 and 1.0 are correct. And finally, a value of the infinite variant. And here we also have a similar syntax rules to the structs. We must list the genetic types of all values and all values containing in every variance of the enum. So here we have a variance containing the type T and the variance containing the types U and V. We must list all three of them in the enum signature. And the option and the result which you are familiar with also contain generics. And here are the declarations for this enum. For the enum option, the sum variance contains a value of the genetic type T, and the non-variant contains nothing. So the option enum, we must also put the genetic type T. For the result enum, the OK variant contains a value of genetic type T, and the error variant contains a value of the genetic type E. So we must put both T and E in the result enum declaration. And let's look at the example in code. Here we have basically have the example, the number example from earlier. We have the enum number with three variants here, and we have an array of those of values of the enum. All of them has the type number, and with generic with concrete types I32, U32, and F32. And the values are basically the same values as we had from the slides. And then we will iterate through this array and print out the values accordingly. Let's try running this and see what happens. So the first element is a 1D number containing the value 5, and it prints out 5. The second element is a two-dimensional number containing the value 2, 1.80, and it here is print out 2 and 1, which is what we expect. And the third one is a infinite number. So it prints out infinite number, which is also what we expect. We can also have generics in struct methods. Here we have an example. Again, we have the example of the struct point with members of type T from earlier. And we have a generic implement block on that. So you can see the syntax here. We need to put the generic type both after the implement keyword and the struct name. And here we have the function x that basically returns a reference to the member x. of the struct. So what this syntax means is that methods in this implement block work on points containing the genetic type T. So that means type T can be anything. It can be integers, it can be float, it can be characters, it can be strings, it can be anything. Wait, so why do we need to specify that the implement block will work on all types T when we know that point can contain all types T? Why do we need a distinction? Well, as it turns out, we can also have implement blocks for concrete types. So here in the example on top, we have an implement block for the struct type, but with genetic with concrete type I32 instead of a generic T. And then here we basically just calculate the distance from origin of point. And here is the formula for that. And above that, we still see the implement block from earlier, where we basically take points with any type and then return a reference to that. And here we change a little bit to return an integer. And do note here that for an implement block for a concrete type, we no longer need to specify the genetic T in the implement keyword because we no longer have a genetic T. We have a concrete type now. But we still need to specify the concrete type for the struct. So we still need to specify that this point has members with type I32. And in the example below, we have 2 points, an integer point and a float point. For the integer point, we give the members the values 3 and 4, and then we calculate the distance from origin. This distance will be 5. And then we have a floaty point, a p float, variable p float here. That is of the type point where members are floats. And we give them the values 5.0 and 10.0. And then we try to calculate the distance from origin. Here, Rust will say that we have no method distance from origin for points with members of type S64. And it will suggest that a method was found for points with members of type I32. So this line of code, this bottom line of code here won't compile. It will be an error because we already defined this function for points containing I32. Let's look at that example in code. So here we see an example from earlier. We have the struct point, we have a generic implement block, and we have a generic implement block that returns a reference to the member X. And we have a concrete implement block for points containing type I32. And we have and that implement block has a function distance from origin. And here we have a floaty point that is a point containing the type I64. And then we will call get X on that and see what the member X is. We'll set another point, an integer point, where members are of type I32. We also try to get the X coordinate. And here we will also try to get the distance from origin. So let's see what this actually prints out. So first we see that the X coordinate of the floating point is 1, which is what we expect. And X coordinate of integer point is 3, which is correct. And the distance of the int point from origin is 5, which is also correct mathematically. Now let's try to get the distance from origin of the floating point. As you can see here, Rust will say that no method was found. This method wasn't found for the type point with for the struct points with type F64. And it will suggest that point containing I32 actually has this method, since we already defined it for points with I32. And lastly, we can have generics in function calls. So here is the example from earlier where we have two functions that do the same thing, except only for arrays containing different types. And now we know the generics exists. We can combine these two functions and just substitute with this generic type with this concrete type with a generic type. And we can also express the same logic for other types if we do that. And on the right is the result that we have. We just have a function largest that takes an input with a generic type t. This input is a reference to an array of t. And we also need to list t in the function name, just as we did with structs, with enums, and with methods. And this function, similar to the other two on the left, also returns a reference to t. And we basically have the same logic. We declare largest to be the first element, and we iterate, get the largest element, and then return. And in the main function, we will try to use this largest function. We have, so in main functions, we declare two vectors. One is a vector of I32 containing the values 1, 2, 5, 4, 3, and we call largest on that and try printing it out. And the other is a vector of characters. We also call largest on that and try printing it out. So now this should work, right? Since this function takes an input that refers to that has a type t, generic t. So you should be able to substitute any type for that, right? Well, no. Rust is actually unhappy about our code. So here we have some pretty weird errors that we need to restrict the generic type t somehow. So the reason here is that what if our t is a hash map? Then we cannot compare elements, right? We cannot compare a hash map to another. So here we actually cannot do this comparison because the concrete type the user input into the function largest, might not be comparable. So if t is a hash map, then this code doesn't work. To fix this, we will explore in a future lecture about traits. Now let's look at the how the error actually play out. And here we basically have that function. And let's try to compile this file. And here we see the same error. We cannot have we cannot have this comparison item greater than largest because type t may not be ordered, it may not be comparable. Next, let's have a look at smart pointers. So as you may be familiar from languages like Java and C++, pointers or draw pointers, as we will call them here, they are variables that contain or point to an address in memory. Smart pointers are basically pointers. They act like pointers with some additional capabilities. For example, the string and the var types, they are examples of smart pointers. So they have a pointer, but with some capabilities, including managing on memory, and they also know the length of the collections they store. So that's the capabilities we are talking about. For a smart pointer, they take ownership, meaning they own the data they point to. So it's very different from the raw pointers you may be familiar with. And when smart pointers goes out of scope, the data they point to is dropped. Due to ownership rules, safe Rust does not allow raw pointers. So most of the pointer-like types you interact in Rust are smart pointers. And a very common one that you use is the boss smart pointer. So a boss containing the generic type T allows you to store data on the heap. So it sounds familiar, sounds similar to React and string, right? Why do we need a boss? Because the data you store on the heap for boss does not need to be a collection. It can be just one value. What does a boss consist of? So like all containers or data structures we are familiar with, boss consists of a raw pointer on the stack that points to some data on the heap. So we have the pointer on the stack here and the data on the heap, and the pointer will point to that. When the stack pointer goes out of scope, the data on the heap is freed, or as we call it, just dropped. Do note that the pointer, this is just a raw pointer, but with some additional capabilities. So the definition we have from earlier. And this capability being that it owns this data on the heap. And how to actually use bosses. So we can create a boss smart pointer using boss colon new, and we just put data inside the function call. If we want to modify the data the boss storing, we just make the boss mutable. And then to access the data, we dereference it. So just like raw pointers in C++. Do note that when calling functions on the data, we don't need to dereference, just does it for you. What does it sound familiar to? Basically a reference, right? So here we have an example of a boss. First, we declare for comparison, we declare a stack integer, and then we just assign the value 5. So this int value 5, it will live on the stack. And then we have a boss that contains a value of type array2, and then we give the integer the value 4. So this integer of value 4, it will live on the heap with a stack pointer pointing to it. And then we try to print out the dereferenced value. It will print out 4 because the value is 4. As mentioned, boss sounds very similar to references. So why do we need both of them? What is the difference? Well, first, similarity. Both of them act like pointers as we have seen, and both ensure that the data they point to cannot be null. So unlike raw pointers. The difference is that the boss actually owns the data it points to. So if you pass a data into a boss, it will own that value. So very similar to a vector in that. Whereas references, they just borrow the data they point to. They don't own anything. And the data is owned by some other variable. It might actually be owned by a boss. So we may have a scenario where we have a boss own a value and a reference to that value. What if we want something similar to nullable pointers in C++? We can grab either the boss or a reference inside an option. So if it's a sum, then we have a valid pointer, and if it's a non, then we have a null pointer. And then again, this also gives us the ability to force check that if the pointer is null. So you cannot forget to check it. And let's look at an actual example of a boss. So here we have the stack in of value 5 and heap in the value 4 from the slice. And then we try to print out the heap integer. And then we also try to print out the sum of these two integers. As we see here, to get the value of the value of the boss, we just dereference it, much like a reference. And then we try to get the square of the heap integer. by calling the function pow with argument 2, so power of 2. As you can see here, when calling a method on the data, we don't need to dereference. And then let's try running it. As you see here, it will print out the value of int is 4, so it's correct. And sum of the ints is 9 because we have 5 and 4 for these two integers. And then the square of the heap integer is 16 because the heap int is 4. So why do we need bosses? We need bosses when you have a type whose size cannot be known at compile time. So you don't know the size of the type at the time your code is compiled, but you still want to use a value of the type in a context requiring an exact size. So for simplicity, just think of this context as anything involving the stack. Since anything on the stack, the compiler needs to know the size of the values at the time the code is compiled. Conceptually, the reason we can bypass this requirement is that the size of the stack pointer will be treated as an exact size that the compiler wants. This is also why the vector and string types exist. We may not know the size of the array yet, but we can have a pointer on the stack used by both vec and int to point to that array. And so we can bypass this requirement. An example use case we will look at is implementing a linked list. First, let's create a naive implementation. So a linked list is basically a chain of data where each node has a pointer to the next node all the way until the last pointer points to nothing. Yeah, so you may be familiar with this data structure from CS.28. The first implementation we will look at is we basically copy our implementation from C++. So we have the struct link, that is each node here, that stores the thing, that is the data each node store, and then the next pointer. So here, again, we emulate nullability by wrapping the pointer in an option. So the next member can either be a link, that is the next node in our linked list, or it can be none. So there's no next node, as you can see in the diagram here. Well, we have a problem with that. So here, if you look at the error message for this, you can see that Rust tells us that we have a recursion without indirection. And we have to insert some indirection to make link representable. And you also say that recursive type has infinite size. So what does all of this mean? First, let's look at the implementation again. So what we actually have here is that each link will store another link inside of it. So that's why it just says there's no indirection. So the link can store nothing, but it can also store another link. So the problem here is that the Rust compiler does not know if when this infinite storing link will actually stop. It may stop after like 3 links, 4 links, 5 links, or it may never stop. So yeah, Rust cannot know the exact size of link since the link can either store another link inside it, or it may not store anything. And since link lives on the stack, since we don't use any smart pointers, we don't use moss, we don't use vector, we don't use string. This a link will live on the stack by default. So this entire thing here will live on the stack by default. That is a context involving the stack. So this implementation is forbidden since Rust doesn't know the size of link and link lives on the stack. What is our solution here? Well, As we see from the examples of smart pointers, we can bypass this requirement by having a pointer, by just having a singular pointer on the stack and everything else elsewhere on the heap. And BOS comes into play. So here, instead of this option containing a link, we insert a BOS in the middle. So this link will be contained in a BOS. That means that we have a pointer on the stack that points to another link on the heap. Or in the case of the second node onward, we will have pointers on the heap point to other locations on the heap. And then the option to represent nullability, meaning we can either have a valid pointer or we have a null pointer for the non case. Here we achieve indirection. That means that instead of from earlier where we have a link, the storing other links indefinitely, here on the stack, we only have a singular link. And every other link will live on the heap, and they will be separated by a pointer that is a BOS. So since on the stack, we only have a singular link, so we just have the data, and then we have a singular pointer that is a BOS. This code will compile, and it will be a valid linked list implementation. And the explanation is that due to this indirection, Rust will determine the exact size of the struct on the pointer as the first BOS stack pointer plus the size of the data. So we have a finite size that Rust can figure out instead of an infinite recursive type that Rust does not know when it will terminate. And this is a valid linked list implementation. You could further explore this linked list implementation in Homework 8, where you will also work with a linked list. And that's all for today.